Hi everyone, we're just looking through chapter 32 here on particle physics. Just to emphasize, the chapter 31 on nuclear physics is obviously going to be a very important part of this chapter. So it might be worth looking back over that material before we carry on. Particle physics concerns the sub-nuclear, I suppose, or certainly the subatomic level of physics. So things smaller than an atom and even smaller than a proton or a neutron. Um, it's really what is the composition of matter is trying to answer that question. And it's still a developing field. We've got a very, very good picture of what the world looks like on this tiny, tiny scale, but it's certainly not perfect, and we're still answering questions with it. Some of the things we do know for sure is that we'll be working with these two concepts, the fundamental forces of nature and the conservation laws. So we've met plenty of conservation laws before. Hopefully there'll be no surprises that they're with the conservation laws. The fundamental forces of nature, we've discussed some of them. We haven't actually discussed all of them, but I'll just start off by saying we really do need to understand what's in this table 32.1. And that is the four fundamental forces of nature, which are gravity, we've met plenty, the electromagnetic force, we've met plenty. The strong nuclear force, I think I've discussed in class, but the strong nuclear force is the force that allows the nucleus to stay together, even though, if you think about it, within the nucleus, if you've got two protons, that's two positive charges, according to the electromagnetic force, they should be repelled. They should be pushed away from each other, but they're not. So the strong nuclear force is what allows a nucleus to stay together. The weak nuclear force, um, we'll discuss it when we look at beta decay. That's this process where a neutron releases an electron and turns into a proton. The weak nuclear force regulates that type of decay. So you don't need to learn any of these numbers off by heart, but you should have a good idea of what's in this table. Okay, gravity and electromagnetic, they both have what's called an infinite range. They're 1 over d squared is how we describe them. They're inverse square laws. And even though as d in that formula gets bigger and bigger, the size of a force gets smaller and smaller, it never actually reaches zero. Gravity affects all particles and attracts all matter. This force, the magnitude is really how strong is this force? And it's a relative strength where they've said if I call a strong nuclear force 1, how much stronger or how much weaker is gravity or the electromagnetic force? Now, don't worry too much about these numbers. They're just to give you an idea of how desperately weak gravity is by comparison to all the other forces. It's a very, very weak force. We feel it strongly because we're surrounded by very large bodies of mass. Okay, so anybody that has mass, like the Earth, for example, will cause a fairly strong gravitational force. But, uh, you know, yourself as a person, you have almost no gravitational field around you because you just have such a small amount of mass because it's such a weak force. Whereas if you were to rub a biro or something against your jumper, you'd have a reasonably strong electromagnetic field around you, one that we can see the effects of in everyday life. So that's actually a much, much stronger force. The reason we don't interact with it very much is because the Earth is neutral. The Earth does not carry a large number of charged particles, which is the only type of particle that feels the electromagnetic force. Okay, it's very important. Yeah, the static electricity stuff that we do obviously is how we study it, but really what's really important about the electromagnetic force is it allows atoms to bond to each other. So chemistry essentially emerges from that force there. So interestingly, the two that we're not familiar with are actually very, very strong forces. The strong nuclear force is the strongest of them. And one of the questions, by the way, you'll be asked in exams is rank these four forces in order of strength. So you might not be asked what's the number for 10 to the minus 38, but you need to know that the strong nuclear is the strongest, then electromagnetic, then the weak nuclear, and gravity is the weakest of the four fundamental forces. By the way, what we mean by fundamental force is that any other force you might talk about in the universe is some manifestation of these. So most commonly, it's the electromagnetic force. If you talk about, a biro sitting on a table, biro here, it's experiencing a downward force, its weight, and then it's experiencing an upward force, which we call the normal force. But that normal force is really just the electrostatic repulsion between the electrons in the biro and the electrons in the table or in the paper. So most forces that we think of are actually electrostatic forces being manifested in some way. And all forces can be explained in terms of those four fundamental forces. So another idea that's summarized in this table, as well as the relative strengths here, is the range across which they act. So we've already mentioned that inverse square law, gravity and electromagnetic force both obey inverse square law, so they have an infinite range. Whereas the strong nuclear force actually has a really, really small range. That's a tiny number, and it's approximately the diameter of a large nucleus. Okay, so the strong nuclear force will allow a nucleus to hold together, something like carbon, no problem. A very large nucleus, like say uranium, for example, is less stable because a lot of the protons and neutrons within it are just further away from the center. So the strong nuclear force has less hold on them, I suppose, which is why we're able to split them open when we do nuclear fission. The weak nuclear force then has an even smaller range. That's about the scale of a neutron. That's about the diameter, if you like, of a neutron. So it operates over a very, very short distance. So the reason we don't see the strong nuclear and the weak nuclear force in our everyday lives is because they operate over such small distances on scales that we have no kind of frame of reference for. So these are the two fundamental forces that I suppose if I were to ask a class, I would expect to see these answers coming back from students. These two you haven't really encountered before, but you need to be familiar with them now, I suppose. Strong nuclear force only acts on protons and neutrons. Weak nuclear force acts on all particles. And then the purpose there, gravitational force, it attracts all matter. Electromagnetic force attracts charged matter, and its purpose is for bonding. Strong nuclear force keeps the nucleus together, and the weak nuclear force, as I said, regulates beta decay. Now, the other, I suppose, important set of rules that we're going to be working with in this section is these conservation laws. Okay, so the conservation of mass energy, if you remember, our junior cert conservation of energy rule changed with E equals mc squared mass energy equivalence. We now say conservation of mass energy rather than conservation of just energy. Momentum is also a conserved quantity, and electric charge. So in any interaction, while charge might move from one body to another, or momentum might move from one body to another, it might convert, but it does not disappear or just appear out of nowhere. It can't be created or destroyed, but only changed. Okay, so that's the general rule for conservation laws. Sorry, E equals mc squared. We've seen down there, that's going to come up again in this chapter. I know we saw it in the last chapter as well. So what I'm going to suggest you do there is just read pages 364 to 367 yourself there. And I'm going to jump in and have a look at exercise 32A on page 378. And we're just going to do question 1. I'm going to leave you to do question 2 yourself. They've given us a bunch of constants here. These are in the log tables as well under fundamental physical constants, and they've given more of them here. So very often they'll give you these constants in questions, but occasionally you do need to look things up in the log tables. Page 46, fundamental physical constants, and also page 48, particle physics will have a lot of values that you'll need in this chapter too. So in beta emission reaction, in a beta emission reaction, carbon-14 can decay to nitrogen-14 with the emission of a fast-moving electron. If 0.01% of the energy produced from the loss in mass is converted to kinetic energy of the beta particle, remember, is just an electron, calculate the energy in joules and in electron volts and determine the velocity of that beta particle. Okay, so this is a conservation of mass energy problem. We'll just get into it now. This is the reaction they're describing. Okay, carbon-14 is decaying to nitrogen-14, and this is how we date old pieces of organic matter, like an old piece of wood or anything like that. We can date it using carbon-14 dating. Nitrogen-14 and gives off a beta particle. That can be written as a beta or as an E minus. And with all these reactions, there's a release of energy. Okay, but remember, the energy released is equivalent to the, in inverted commas, lost mass. So that's the first thing you need to work out is, well, carbon. So what happened, by the way, is one of the neutrons has converted to a proton. Okay, so the mass doesn't change because you still have the same number of neutrons and protons. But here, where you have maybe 8 neutrons, here you've only got 7 neutrons and you've got an extra proton. And the atomic mass in whole numbers doesn't change. In the decimals, it does change a little bit. And that's what we're going to look for. It's also, this electron is given off. Okay, so charge is conserved because an electron can be written as -1, 0. We treat it as, on this scale, having a mass of 0 because it's so small, and its charge is -1 plus 7 makes the 6 here. So charge is conserved throughout, and the lost mass, I'll just do that now. Okay, I'm basing this off these two values here, plus the mass of the electron. Just note we've been given our mass for carbon 14 and nitrogen 14 in atomic mass units. So we're going to have to look that up under fundamental physical constants, whereas mass of the electron was given in kilograms. So just be careful about mixing units. So to start with, our change in mass from the carbon, which was 14 atomic mass units roughly, to the nitrogen, which was just shy of 14 atomic mass units, is 0.004007 atomic mass units. That's not kilograms. Okay, so that's kind of the missing mass. Now, some of that is this beta particle, but remember, we've got that in units of kilograms, so we need to convert this to units of kilograms. If you go to page 47 in your log tables, you'll see here the unified atomic mass unit is given here 1.66 times 10 to the minus 27 kilograms. So working with that figure, I can work out how many kilograms of mass is there in difference between carbon and nitrogen. Okay, so our difference in mass then is the number of atomic mass units multiplied by the value of one atomic mass unit in kilograms, which gives us 6.6 times 10 to the minus 30 kilograms. So that's our difference in mass between carbon 14 and nitrogen 14. Now, that's not the only thing that's changed. We have to account for our beta particle as well. So the missing, in inverted commas, mass is going to be that I'm going to change that to 6.65 times 10 to the minus 30, minus the mass of the electron, which is 9.1 times 10 to the minus 31. And what's that going to give us? You see it there, 5.7 times 10 to the minus 30. So that's our missing mass. And we can work out the energy released then using E equals mc squared. Okay, so that's our missing mass, 5.7 times 10 to the minus 30, times our speed of light, which is given in this, I think, as 3 times 10 to the 8. They haven't asked us to work any more accurately. Yeah, 3 times 10 to the 8. So I'll stick with that squared. E equals mc squared. So I'll take that, multiply it by 3 times 10 to the 8 squared, and I get 5.17 times 10 to the minus 13 joules. The question also asks us to give that energy in electron volts. So to get there, you divide by the charge in the electron. That's in electron volts, it's going to be 5.17 times 10 to the minus 13 divided by, given in the question there, 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19 coulombs. Minus 19. The unit here is in coulombs, but anyway, that divided by 1.6 times 10 to the minus 19 gives us 3 3,230,878 electron volts, or 3.2 giga electron volts, 2.3 GeV, giga electron volts. Okay, so that's a huge amount of energy. It said 0.1%, 0.01% of that energy is converted into, is given to the beta particles. So multiply that by 0.0001. Okay, so that's 0.012. Move the decimal place 2 places, I suppose. 0.01%. And you're getting yourself 232 electron volts. Excuse me, we really should have been working with joules. So let's go back to our 5.17 times 10 to the minus 13 times 0.0001 gives 5.17 times 10 to the minus 17. Yeah, could have guessed that actually. So 0.01% equals 5.17 times 10 to the minus 17 joules. And the question then is, well, what was that's the kinetic energy of the beta particle, okay? And the question asked for the velocity of the beta particle. So to finish up, we need to say that 5.17 times 10 to the minus 19 being used for another lesson. 5.17 times 10 to the minus 17 is, well, kinetic energy is a half mv squared. So that's the velocity we want. We know the mass of the electron. It's given in the question there, 9.1 times 10 to the minus 31. Half of that, so divide by 2 times the velocity squared. So this is what we need to solve. Multiply through by 2 times 5.17 times 10 to the minus 17, and divide through by 9.1 times 10 to the minus 31 is v squared, and v is going to be the square root of all of that. That's as 1.07 times 10 to the 8 meters per second, which is about 1/3 of the speed of light, which is always kind of a good way to think about your answers in these things. If they ever go faster than the speed of light, you've done something wrong. But that's a huge amount of energy. On the scale of electrons, 3 giga electron volts is a really, on the scale of, electrons, yeah, that's a really huge amount of energy. So it gives it a very high velocity, even when only a very small fraction of that energy is actually converted into kinetic energy. Okay, I'm going to leave it there. I'm going to ask you to try question 2 yourselves.